Okay, so I want to sketch out essentially why the normal distribution comes up as the sum of lots of small errors in this result, which we discussed already, called the central limit theorem. Okay, so I'm going to kind of sketch out, discuss two results, one called the law of large numbers, which I think we've already discussed as well, and in fact I'll prove probably in a later video. So law of large numbers and the central limit theorem. Oops, the central limit theorem. And here, I'm not going to be super rigorous, but I just want to get across the idea to you why this normal distribution, this sort of funny e to the minus x squared type of function, is turning up. Alright? So the idea that I want to kind of get across is I want to explain. So I want to explain, let's not say I'm going to, but let's say I want to explain why the normal distribution is so important. Okay, so suppose we're going to do an experiment lots of times and I'm going to count the number of successes. So suppose, just like we did at the beginning of the course, I throw a coin 100 times, okay, and count the number of heads. Okay, so in particular, I'm going to let S of 100 be the sum from I equals 1 to 100 of xi, where xi is a result of the ith coin throw, where xi is equal to 1 if ith throw is heads, okay, or 0 otherwise. Okay, so as we know, the proportion of heads should, we'd expect, be close to its mean. Okay, so in particular, if I look at the sum of the number of heads divided by the number of coin throws, this should be approximately equal to half, okay, which is the expected value of each of these x's. Okay, so for each of these xi's, the expected outcome is a half, assuming the coin is unbiased, and so the proportion of heads should be roughly equal to half. Okay, now we imagine this is quite close to half for 100, and for if we did 10,000, it should be even closer. Okay. Now this is a result that can be proven mathematically, and it's a result called the law of large numbers. Okay. So this can be shown mathematically. Okay. So there's a theorem. Okay. And we're going to discuss just here the weak version of this theorem, called the weak law of large numbers. Okay, and as you might expect, there's going to be a stronger version of the law of large numbers as well. Okay, and it basically says, not just for coin tosses, but for independent mean mu random variables xi, okay, for I as big as you like, for I equal 1 to n, with, as before, Sn just being the sum of these random variables. So just sum up a whole bunch of random variables xi, okay. Then, for all numbers I like, by this I mean any small number I like, the probability, okay, that the average of all this sum is less than or equal to mu plus epsilon, okay, and bigger than mu minus epsilon. So imagine that epsilon being something really small, like 0.00001, okay, so some really small value. So we could imagine mu here in our coin tossing case is a half, okay, so we're asking, well, what's the chance that, let's say, you know, after 10,000 rows, that the average that we've observed so far, okay, is between, let's say, 0.499 and 0.501, okay? All right, so that's the sort of question we're asking here, okay? So what's going to happen to this, as we might expect, is if we get n really, really large, this should get closer and closer to mu, all right? So the likelihood that we observe the mean, this sort of empirical mean that here, being outside of this interval, so being less than mu minus 1, and bigger than mu plus 1, should get really, really small, okay? So the chance that we're actually captured it within this interval, okay, is going to get closer and closer to 1, okay? Now this makes sense. I mean, this is what should happen, shouldn't it? If we've got lots of independent experiments and we look at the average, well, the average should get close to what we expect to happen, mu, all right? So in some sense, the weak law of large numbers, you could think of as a bit of a tautology, really. You would expect this to happen. In fact, when we started discussing the course at the beginning, we were saying that, you know, we think of a probability as just the sum of the number of successes divided by the number of experiments. And we're really just doing the same thing here, okay? So it makes sense that this result should hold. That said, we're able to prove this just using our laws of probability, that the probabilities are positive, that they sum to 1, and then we have this notion of independence. And with just those properties, we're able to show this result. So we're not adding to our sort of model the idea that this result should hold, but by the assumptions that we have about probabilities and the assumptions we have about independence, it must be that this result holds. Okay? Okay. So that's enough about the weak law of large numbers. We'll give a proof of it a bit later. Okay? But that's not what I'm here to discuss, really. So given that we know that Sn divided by n is going to get closer and closer to mu, there's going to be some error involved, and we want to understand exactly what that error is. So, okay. So we know Sn divided by n is close to mu, but there is going to be some error. So let's say I throw a coin 10,000 times, okay? The likelihood that I get exactly 5,000 heads is quite unlikely, actually. So there's always going to be a little bit of error, you'd imagine. All right. So we want to kind of study how that error happens. So let's define epsilon n just to be equal to Sn divided by n minus mu. Alright? Which I can also write out as follows: Sn divided by n minus n times mu divided by n. Right? It's just another way of writing that out. Okay? So, what does epsilon n look like? We know that this epsilon of n is sort of going to 0 as n goes to infinity. Right, that's sort of what the weak law of large numbers is saying. Okay, but how fast? Okay, we can use one of our calculations before to get an idea of what's happening to this. So if I look at the variance of this epsilon n, this error, okay, well, it's equal to the variance, okay, of Sn minus n mu divided by n, right? So well, we know one thing: if we have a random variable a times x, so we multiply random variable x by constant a, then it's just equal to a squared variance of x. Okay, so I can use that here. That's my kind of x, and this is 1 divided by n is my a. So this is equal to 1 over n squared, the variance of Sn minus n mu. Okay? And then, well, I can look at this a little bit further. So I've got 1 divided by n squared, the variance, okay, and I'm going to remind myself that Sn is just going to be a sum. I'm going to stick to the case where it's the sum of a bunch of Bernoulli random variables for simplicity. Xi minus mu. Okay, so I'm just using the fact that Sn, like up here, or like up here, it's just the sum of a bunch of 0, 1 random variables. Okay, actually we don't need these random variables to be 0, 1, but that's by the by. For now, let's just stick with this case when we're looking at these errors. Okay, so well, well, we know for independent random variables, okay, that the variance of the sum is the sum of the variances. Okay, so we proved that before. Okay, so notice I can take this sum outside, and it's equal to the sum of I equals 1 to n, the variance of xi minus mu. So remember, that's because the variance of x plus y is equal to the variance of x plus the variance of y if x and y are independent. Okay. Okay, so let's keep going. I'm going to assume that xi is a Bernoulli random variable like before. Okay, I'm going to assume, and specifically, we're throwing an unbiased coin here. Okay, just to make things a bit easier, and you can check for yourself that each of these variances is equal to 1/4 in that case, right? So then, and if it wasn't a Bernoulli random variable, we'll just end up with sigma squared here. Okay, but anyway, let's stick to the case of a quarter, right? So we're going to end up adding up n random variables, all with the same variance. Okay, so we're going to end up with 1/4 times 1 over n. Okay, because we're going to get an n for this, and we're going to divide it by n squared, so I'm going to result with 1 divided by n. Alright? Okay, so what that's telling us, if we think of the variance as being sort of the square of the distance, notice that the standard deviation of n is equal to about 1 divided by 2 square root of n. Right? So the error here is going down at a rate that's about 1 over square root of n. Alright? So then, as we discussed before, that means if I had 10,000 coin throws, okay, 10,000 is 100 squared, so we expect an error of the order of magnitude of about 100. Okay? So let's investigate that a little bit further. So this, just to write that down, so this implies, well, let's just do the following. Oops. Notice if I multiply my variance here, okay, by this standard deviation here, alright, so if I times by square root of n, okay, times 2 epsilon n, right, then the variance of this error is equal to 1, because I can multiply this out, I'd get 4 times n, which would cancel out with this guy here. Alright, I'll tell you what, I'll just write that out explicitly. So if I look, so the variance of 2 times square root of n times this error is equal to 4 lots of n, the variance of epsilon n, which is equal to 4n times 1/4 times n, which is equal to 1. Right? So somehow, if I multiply by 2 square root of n to this error, okay, the difference away from the mean here, notice it stays sort of about the same. Right? The variance stays about the same, which is saying that sort of the distribution's not spreading out and it's not concentrating, it's sort of staying fixed, it's sort of staying balanced somehow. Alright? So if I times by square root of n, I'm not expecting a distribution of errors that are kind of growing. I'm not expecting the distribution of the error to kind of concentrate either. Alright? So what that's sort of suggesting, this sort of suggests that Zn, which I'm going to take to be, well, I'll tell you what, I'll stick this sigma back in. Notice this is going to be sigma here. Right, 2, in the case of this, this is equal to 1 over sigma in the case of a binomial distribution. Okay, anyway, Zn equal to square root of n divided by sigma epsilon n, okay, which is in this case equal to Sn minus n mu, okay, divided by sigma square root of n, okay. So if I look at this, okay, it suggests that this does not go to 0. And that's because the variance, as we've seen above, of Zn is equal to 1 always. Alright? So in some sense, as I let n get larger and larger and larger, okay, and I look at the error away from the mean, it's somehow not spreading out and it's not concentrating towards 0. Right? It's just sort of staying balanced. Okay? And the question is, what is that kind of balancing distribution? As you probably already guessed, what's going to happen? Okay. So the question we ask is, what happens to Zn? And the answer, as you might expect, is Zn converges to a normal distribution. In fact, a standard normal distribution. Right? So that might seem a little bit cryptic at this point, so I'm going to maybe step back for a second because we've done a fair bit of maths there. So I'll go back to these calculations here. Right? So here, what I'm doing is I'm going to compare, summing up a number of Bernoulli random variables. Okay, so like I was doing there, so I'm going to take 10 coin tosses, okay, having a probability half, and I'm going to look at the probability distribution associated with that. Okay, so notice this is going to be a binomial random variable. I'm going to look at the probability mass function of that binomial random variable. Okay, I'm going to compare that to the probability density function of a normal distribution. Okay. So I'm going to look at what the probability mass function looks like, the distribution when I sum up a number of coin tosses, okay, and I'm going to compare that to the normal distribution with the same mean appropriate variance. Okay, so I'll tell you what, I'll start with a slightly lower number. Let's start with, okay, so let's do 4 to begin with. Alright, so if I look at 4, okay, that is each of these points here in the blue line is giving the probability density function associated with the normal distribution for that. And these 5 points are the binomial distribution for that. Okay. Now let's go a little bit bigger. Let's go up to 10. Okay. Now it looks quite a bit closer. Okay, so the line here is plotting a normal distribution. Okay, and the points plotted here are the points of a binomial distribution. Okay, and you can see it's a pretty good approximation already. Right, let's go a little bit further. Let's go to like 30. Right, it looks very close. Right, so if I toss 30 coins, actually the distribution around the mean already is looking very close to a normal distribution. Right, so I didn't even need to go to 100. You can go to 100 if you like. If we go to 100, it's even going to get even closer. All right, so you see that actually the error away from the mean as given by a binomial distribution is actually very close to a normal distribution. All right, even though the normal distribution is a continuous distribution and the binomial isn't, okay, the approximation between the two gets closer and closer. Okay, in fact, this is true for any distribution. It doesn't have to be binomial distribution. If I add up a number of random variables, okay, minus off the mean and divide by the standard deviation in the appropriate way, okay, that distribution is going to look very close to normal distribution. All right, so it doesn't matter how the errors occur. If I look at the errors from summing up a bunch of random events, okay, it's going to look very close. Okay, the distribution around the mean is going to look very close to a normal distribution. All right, so this result is called the central limit theorem. Okay, so let's write that down. Okay, so for independent random variables, and let's call them xi, with mean mu and variance sigma squared, and Zn given as above. Okay, so notice that Zn here I've defined to be this, and notice here that Sn is just the sum from I equals 1 to n of xi. Okay, so for this I look at the sum of the random variables, I minus off the mean, and I divide by the standard deviation and also by square root of n. Alright, so looking at how, if I look at what sort of factor, when looked at this sort of square root of n ratio away from the mean, this error is given by, okay, then the probability that Zn is less than some number, let's say z, as n goes to infinity, goes to a normal distribution. It goes to the integral from minus infinity to z, 1 over square root of 2 pi e to the minus x squared divided by 2 dx. Right? So as we're seeing, it doesn't matter what set of random variables I start with, if they've got the same mean and the variance and they're independent, I sum them up, okay, and appropriately renormalize, then that distribution looks like a normal distribution. Okay, so whenever I look at the error away from the mean, okay, provided I appropriately renormalize, then what I'm going to get out is normal distribution. So this is sort of essentially the reason that normal distribution occurs so much. The perturbation of lots of errors, okay, gives a normal distribution. So think of it like this, for example, with the heat example. I mentioned that if you have a metal bar and you apply a heat at one point, then the distribution of the heat should be normally distributed. We could think of it like this, as there are lots of little sort of heat particles moving around, okay, transferring between the molecules in the metal, okay, and assuming they move around at random, okay, what we're going to get is from the central position lots of little errors propagating out, okay, given the eventual location of the heat that originally came from the source, okay. Now what that's doing is just adding up lots of small errors away from the mean, which is where it started from, okay. So that's why we anticipate that something like a normal distribution might be the distribution of heat as it spreads through that surface, okay.